Hey guys, we're going to try to get started here on Chapter 11. We're going to try to cover two sections, which are arc length and sector area. I'm lumping these together because conceptually I think they follow a very similar trend. And so for this video, to keep it short, I cut out a lot of the practice. So I'm going to go through it pretty quickly. So this may be a video that you maybe need to stop or rewatch. Maybe you haven't had to do that with other videos. Maybe you'll have to do this one more. But it's not too bad, but there's just not going to be a ton of extra practice thrown in this video, so we can keep it a little short. So, to start off here, arc length has a lot to do with circumference. So circumference is really just the name for the perimeter of a circle. And so the ratio of the circumference to the diameter is always the same. It's a constant. It is the circle constant. It is pi. Okay, so that's how pi is derived. Pi is the circumference divided by the diameter. And so all we really need to know about circumference is you need to know the formula. So circumference is pi times the diameter, which is 2 pi r, because the diameter is 2 times the radius. So there are circumference questions. Those are just plug and chug. Nothing too exciting there. The way to make it a little more exciting is to bring in this idea of given this tire, how far would it travel if it did 15 revolutions? Okay, so if you imagine taking something that is round, okay, and picture kind of marking where it is. So this has like where this kind of numbering is, and if you were to start to roll this, okay, then what happens is the part that's staying on the ground, okay, kind of spins around when the circle spins, and by the time it spins all the way around, the distance that you've traveled is the same distance around the circle here. Okay, so the only thing that we really need to know to be able to figure this out is essentially that a conversion is that one revolution is equivalent to a linear distance of one circumference. So if you spin something around one time, or roll something around one time, it'll travel a linear distance equal to its circumference, okay? And so this will be solvable just doing kind of unit conversions. So what we need here is, we can add all this stuff up. The diameter here is 26 inches. So if I'm basically going to convert the 15 revolutions to the nearest foot. So unit conversions work like this. You just keep multiplying by fractions that are equal to 1, right? If you multiply by 1, the number doesn't change. So if I'm going to keep this the same, I can multiply by 1. 1 over 1, that would be boring. But the other way you can get to 1 is by 5 over 5, 7 over 7, anything where the numerator and the denominator are equal to each other. And then we kind of work our way through this by making things that are not numerically equal, okay, but are equal in terms of measurement. So for example, here, 1 revolution is equal to 1 revolution. Well, how else can I write 1 revolution? With 1 circumference. And the circumference of this is 26 pi inches. Pi times the diameter. So now the units of revolutions will cancel, and that is how far I've traveled in inches, but I want it measured in feet. So I need one more conversion because there are 12 inches in 1 foot, and now the units of inches cancel, and this will come out to be feet. So this, if I multiply it out and round, is about 102 feet. So arc length is just a portion or a fraction of the circumference. Okay? So this is, the wording is slightly confusing because we've talked about the measure of the arc. So the measure of the arc is equal to the same thing as the measure of the central angle. So the measure of the arcs are measured in degrees, okay? The length of the arc is like if you grab some rope and traced out this end here, and then just measured how long the rope was. So the arc length is an actual linear measurement. The arc measure is a degree measurement, okay? So it's kind of a weird situation where like length and measure are actually two different things. So the actual length of this arc is just a fraction of the circumference. Okay, so if you set up a proportion, then we can get this formula very easily. Okay, so the arc length of arc AB, okay, compares to the circumference of circle P. Okay, so this little piece compared to the whole circle is equivalent to what this little measurement is. So the measure of the arc AB compared to the measure of the whole circle, which is 360 degrees. And so if you are just interested in the arc length, you just need to multiply by the circumference. So you get this formula. So the arc length of arc AB, and I like to put this part in parentheses. So it's the measure of the arc at a 360. So it's just a fraction of the circle times the circumference, which is either pi d or 2 pi r. And that's it. That's the formula. So that relates to some pretty straightforward kind of plug and chug here. So the length, arc length of arc AB is a fraction of the circle. What fraction is it? Well, the angle here is 60 degrees, so the arc is 60 degrees. So it's 60 360ths of the perimeter, which is pi times the diameter, which is 16 pi. And this will come out to be 8/3 pi, and the units here are linear, so it's just centimeters, and that's about 8.38 centimeters. Okay, the other arc measure here, we have the arc length of arc GH is a fraction of the perimeter. That fraction is 120 360th, so it's 1/3 of the perimeter because the angle is 1/3 of the full circle. Radius of 11, so that is 22 pi centimeters. So this ends up being about 22/3 pi. Again, linear measurements. That's about 23.04 centimeters. Okay? And so that's it for arc length. Arc length is just a fraction of circumference. So it is a linear first degree measurement. Now, sectors are two-dimensional. So we're dealing with area. Now, the area of a circle, you should know already, is pi r squared. So sectors are just a kind of they're really just a pizza slice, okay? So sectors, okay, a sector is a region in a circle, or a region of a circle, bounded by two radii. Okay, so if you have two radii, so you have two radii and then a piece of the circle, an arc. Okay, and so those three sides, so to speak. Okay, even though this part is curved, those three things make up a sector. It has two straight edges and one curved edge. And hopefully you have a little piece of deja vu because we have a very similar situation here. So this pizza slice is just a fraction of the whole circle. So the area of sector APB is some fraction of the area of circle P, and that fraction is equivalent to whatever fraction is cut out of that circle. Okay, so the measurement of this arc compared to the measure of the whole circle, which is 360 degrees. And again, if you multiply by the area, we get our formula. So the area of the sector APB is a fraction, the measure of AB over 360 is a fraction of the area of the circle, which is just pi r squared. All right. So as you can see, this formula So the sector area is just a fraction of the area of the circle. The arc length is just the same fraction of the circumference. Okay, so these things are very similar. You just got to keep track of what is one-dimensional and what is two-dimensional. All right, so for this example, you could use the formula, okay, but in that case, you'd be solving for r, and then you'd be plugging r back in to find the area of the blue circle. So this might be faster to just use this idea up here. So the area of the sector compared to the area of the circle is equal to the measure of the arc compared to the total measure of 360 degrees. So if I solve this for the area of the circle, this thing down here, okay, if we do the cross products, it'll be this product divided by this measurement. So this area times that is equal to the area of the sector, which is 35 times 360, and then that's divided by the measurement of TU, which is 40 degrees. And this comes out to be 315 square meters. All right. And the last thing here, find the area of this figure. This is a what we call a composite shape. And so the best way to come up with the area of the composite shape is to find the individual areas of the smaller shapes and just add them together. Okay. So in this case, you have a sector. This sector is actually a semicircle. So this total area is just the area of the semicircle plus the area of the triangle. So the semicircle and the triangle make up my major shape. So for the area of the semicircle, all right, if you were to actually use this formula, which you don't need to do, the measure of the arc is 180 degrees. Okay, so 180 to 360, that just comes out to be half. But you could have guessed that because you could clearly see it's half a circle. It's a semicircle. So it's 1/2 of pi times the radius squared. The radius in this case is half of 7. And then the area of the triangle is 1/2 base times height. Because it's a right triangle, I can use the legs as the base and the height, because the most important thing is for the base and height to be measured perpendicular to one another. So the area of the triangle is 1/2 base times height. If you want the exact answer, it's pretty wild. So it's 49/8 pi plus 49 halves. These things can't be added because this has a pi, this one does not. So who knows what this number is? So we're probably better off just going with this approximation. This is about 43.74 square meters. Okay, so that's it. Sector area is just a fraction of the area of the whole circle, and arc length is just a fraction of the circumference of the whole circle. Good luck.